In this video, we are going to show this result using the Feynman's trick, right? We are going to show that this integral is equal to pi over 2 times the ln of 1 plus a. So the Feynman's trick is taking the derivative under the integral sign, right? So we are going to differentiate our integral, that is I of a with respect to the parameter a, right? And I'll do the same thing to the right hand side, and that is going to be the partial derivative with respect to the parameter, that is the tan inverse of a times the tan of x, right? All this one is divided by the tan of x, right, dx. Now, just to refresh your memory, right, so if I'm differentiating with respect to the parameter of something like this, the tan inverse of a times x, this is the same as 1 all over the square of that a squared x squared plus 1, and I'm going to multiply by the derivative of this with respect to a, which is x. So we are going to apply that same principle here. Differentiating this is I prime of a on the left hand side, and that is the integral from 0 to pi over 2 of, this is now 1 all over a squared times the tangent square of x plus 1, and this is multiplied by the tan of x at the bottom, that is this one. And now I'm going to multiply by the derivative of this with respect to a, and that is the tangent of x dx. Cool. So this one is going to cancel this one beautifully, and what you are left is this. So we have I prime of a is equal to the integral from 0 to pi over 2 of 1 all over a squared times the tangent square of x plus 1 dx. Now here I'm going to do a substitution, right? I am going to let y to be equal to the tangent of x, right? So here x is going to be equal to the tan inverse of y, so that implies that the x is equal to 1 all over 1 plus y squared dy, right? So I am going to replace this one with that, and now the change in limit, when x is equal to 0, the lower limit y is going to be equal to the tangent of 0. Tangent of 0 is 0. And when x is equals to pi over 2, the upper limit y is equal to the tangent of pi over 2, and tangent of pi over 2 is infinity. Now the integral in the y world will look like this, that is I prime of a is going to be equal to the integral from 0 to infinity now of 1 all over a squared times tan of x is y, so tan square of x is y squared plus 1. This is multiplied by dx, and dx is 1 all over 1 plus y squared dy, that is dx from here. So the integral I prime of a is the integral from 0 to infinity of 1 all over a squared times y squared plus 1. This is multiplied by 1 plus y squared dy. So now this one, we can now use partial fractions, right? I'm going to use partial fraction to split this one. I have 1 all over a squared y squared plus 1. This is multiplied by 1 plus y squared. Partial fraction, because these ones are quadratic terms, the numerators are going to be linear terms. So I have ay plus b all over the first one, a squared y squared plus 1. Plus the next one is going to be a linear term, which is cy plus d divided by the quadratic term 1 plus y squared. So we now have to find the values of a, b, c, and d. So 1 all over a squared y squared plus 1 multiplied by 1 plus y squared. This is equal to doing cross multiplication, ay plus b, this is multiplied by 1 plus y squared. And then cy plus d, this is multiplied by a squared y squared plus 1. All this one divided by the LCM, which is a squared y squared plus 1 multiplied by 1 plus y squared. So the denominators are the same, right? So let's look at the numerators. So we have 1 to be equal to, now let's FOIL these ones, right? So that is going to be ay plus ay to the third, right, plus b plus by squared. Now the second one is going to be a squared c times y to the third plus cy plus a squared d times y squared plus d. So this is what we have after the expansion. And now let's gather like terms. We have a plus a squared c. All this one is multiplied by y to the third. That is this one and this one, bringing them together and factorizing y to the third. And then for the y squared terms, we have b and then a squared times d. This is y squared. That is this one and this one. Next is the y terms. So that is going to be a and then c. That is ay and then cy, right? And then constant terms, you have b plus d. Cool. Now let's compare both sides. So we have four equations now. A plus a squared c. This is equal to 0. There is no coefficient of y to the third on the left hand side. Next one, b plus a squared d. This is equal to 0 as well. There is no coefficient of y squared on the left hand side. Next is a plus c. This is equal to 0 as well. There is no coefficient of y on the left hand side. And the constant term b plus d is equal to 1. The constant term on the left hand side is equal to 1. Alright. Now solving these four equations simultaneously, these will be the values of a, b, c, and d that will satisfy all these four equations. So a is going to be 0, b is going to be equal to negative a squared, right? Negative a squared all over 1 minus a, right? Like this. We have c to be equal to 0 and then d to be equal to 1 all over 1 minus a squared, like this. So these are the values of a, b, c, and d that will satisfy all these four equations. Now that we have this, we can go back to our partial fractions, that is from here, right? And then we simplify it out. So we have 1 all over a squared y squared plus 1. This is multiplied by 1 plus y squared. So 1 plus y squared. This is equals to, we have ay plus b, right? So we have ay, so a is 0, so we have 0 times y plus b, and b is negative a squared all over 1 minus a squared. This one is divided by a squared times y squared plus 1, right? And then plus cy plus d, that is cy plus d divided by 1 plus y squared. C is 0, so we have 0 times y plus d, and d is 1 all over 1 minus a squared. All this one divided by 1 plus y squared. Alright, so this one is equals to, this is the same as negative a squared all over 1 minus a squared. This is multiplied by 1 all over a squared y squared plus 1. Right, and then plus 1 all over 1 minus a squared multiplied by 1 all over 1 plus y squared. This is the same as 1 all over, it's the same as 1 all over a squared y squared plus 1 multiplied by 1 plus y squared, like this. So now the integral, so we are now going to have the integral, which is I prime of a. So when we go back up, so I prime of a is going to be the integral of that is this one, right? So I prime of a is equal to the integral from 0 to infinity of this, which is 1 all over a squared y squared plus 1 times 1 plus y squared dy. This is the same as the integral from 0 to infinity of this, because they are the same. So we have negative a squared all over 1 minus a squared times 1 all over a squared y squared plus 1. And then plus 1 all over 1 minus a squared times 1 all over 1 plus y squared. All this one dy, like this. Alright. I prime of a is equal to, now let's split this one into two different integrals. We have the integral from 0 to infinity. This one is a constant because that's nothing to do with y, so I'm going to bring it out here. Negative a squared all over 1 minus a squared, and this is multiplied by, so let me write it here cleanly. So we have negative a squared all over 1 minus a squared. Then the integral from 0 to infinity of 1 all over a squared y squared plus 1 dy. Next one is plus the integral, plus 1 all over 1 minus a squared, because this is a constant. Then we have the integral from 0 to infinity of 1 all over 1 plus y squared dy. So I prime of a is equal to what really? So this is negative a squared all over 1 minus a squared. And then the integral from 0 to infinity of 1 all over, here you can factorize a squared out. And that is going to be left with y squared here plus 1 over a squared, like this, dy, plus 1 over 1 minus a squared. The integral from 0 to infinity of 1 all over 1 plus y squared dy. Alright, so we can factorize 1 over a squared out. And when we do that, this 1 over a squared, when it comes out, is going to cancel with this one. So what we are left is negative 1 all over 1 minus a squared. Then the integral from 0 to infinity of 1 all over y squared plus 1 over a squared can be written as 1 over a, like this. All this one squared, like this, and then dy plus 1 all over 1 minus a squared. Then the integral from 0 to infinity of 1 all over 1 plus y squared dy. So this one is just the tan inverse of y, and that is when you are differentiating. But this one, the arctan integral, if you have the integral of 1 all over a squared, or let's say x squared plus a squared dx, this is the same as 1 over a times the tan inverse of x over a, right? So now let's solve the first one using this. So this is I prime of a, and that is equals to negative 1 all over 1 minus a squared. And then this one is 1 all over a is 1 over a, and then the arctan of y over a is 1 over a. The limits of integration from 0 to infinity, and then plus 1 all over 1 minus a squared, and then this one is the arctan of y. The limits of integration from 0 to infinity. I prime of a is equal to, the reciprocal of this is a, so we're going to have negative a all over 1 minus a squared, and then we have the tan inverse. So now let's take the limit. The limit as y approaches infinity of the tan inverse of a times y, right, minus, as y is approaching infinity, this is going to be approaching, as y is approaching 0, this is going to be 0, and tan inverse of 0 is 0 for the lower limit, plus 1 all over 1 minus a squared. And then the limit, right, the limit as y approaches infinity of the tan inverse of y, like this, and lower limit is 0 as well. I prime of a is equal to, as y is approaching infinity, this is going to be approaching infinity, and tan inverse of infinity is pi over 2. So this is multiplied by pi over 2 plus 1 all over 1 minus a squared, and this is pi over 2 as well. Alright, so I prime of a is equal to what really? So that is going to be pi over 2, and then this is going to be multiplied by 1 all over 1 minus a squared minus a all over 1 minus a squared, like this. Okay, so this is what we have now. The next task is to now find a. We want I of a, not I prime of a. So what I can do is to take the antiderivative of this. So the antiderivative is the integral of the I prime of a with respect to the parameter a. And I'm going to do the same thing here. So this is pi over 2. Then I'll have the integral of, okay, permit me to write it like this again, which is negative a all over 1 minus a squared, like this, plus 1 all over 1 minus a squared, like this. And then I'm going to have this one dA as well. Okay, so the antiderivative of the I prime of a is I of a, which is what we wanted. And then we have pi over 2, which is a constant, And then I am now going to integrate negative a all over 1 minus a squared. So I have negative a all over 1 minus a squared like this, dA, and then plus the integral of 1 all over 1 minus a squared, dA, all multiplied by pi over 2 in front. And now this one, I am going to multiply this one by 2 and then divide the integral by 2 like this, to cancel the effect. And now we also know that if we are integrating, so if we have the integral of 1 all over 1 minus x squared dx, this is the same as the tan hyperbolic inverse of x, right? So this one is just the tan hyperbolic inverse of a. All right, so here I of a is equal to, this is pi over 2, which is multiplied by 1/2. The derivative of this one is just the numerator, which is negative 2a. So the integral is just the ln of 1 minus a squared, like this. And then plus this one is the tan hyperbolic inverse of a, that is from here. Right, we are done. We can put the constant of integration, which we will find later on. So this one is equal to what? So I of a is equals to, this one is, permit me to write what tan hyperbolic inverse of x is. So the tan hyperbolic inverse of x, this one is the same as 1/2 times the ln of 1 plus x all over 1 minus x. This is the tan hyperbolic inverse of x. So now let's replace that in our integral. We have pi over 2. This is multiplied by 1/2 the ln of 1 minus a squared. And then plus the tan hyperbolic inverse of a is going to be 1/2 the ln of 1 plus a all over 1 minus a, like this, plus the constant of integration. Alright, so I of a is equal to pi over 2. And then here we are going to do some manipulations here. This one is ln of, these are difference of two squares, this one, which can be written as 1 minus a multiplied by 1 plus a, correct? And then plus 1 over 2, and then the ln of this one, using the laws of logarithm, that one can be written as the ln of 1 plus a minus the ln of 1 minus a, like this, all multiplied by 1/2 plus the constant of integration. I of a is equal to pi over 2. And then now applying the laws of logarithm here, this is the ln of something times another thing, right? So that is going to be 1/2 the ln of 1 minus a, and then plus 1/2 the ln of 1 plus a, using the laws of logarithm. Let's distribute in half here. We have 1/2 ln of 1 plus a minus 1/2 the ln of 1 minus a, like this, and then plus the constant of integration. Will there be any cancellations? So we see that ln of 1 minus a is going to cancel the counterpart here, right? Beautiful. Now I of a is equal to pi over 2 in front, and that is going to be multiplied by half of this plus half of the same thing is going to be ln of 1 plus a, like this, plus the constant of integration. But we now have to find what this constant is, right? So now let me switch colors. If we have I of 0, so we are going to put c to be equal to 0, right? So I of 0 here is going to be equal to pi over 2 the ln of 1 plus 0, right, plus the constant of integration. So I of 0 is going to be equal to pi over 2 times the ln of 1 plus c. But I of 0 is going to be equal to, ln of 1 is 0, so we are going to just have c. But what is I of 0? So let's go up, right, to find what I of 0 is. So to the very top, from the very beginning, right, from here, this is our I of a, right? So when we plug in 0 here in place of a, what are we going to get? So that is going to be the tan inverse of 0 times this one is going to be 0, and tan inverse of 0 is 0. So from our original integral, I of 0 is equal to 0. That is from our original integral. So when we go to the bottom here, we have c to be equal to I of 0, and I of 0 is 0. So the constant is equal to 0. That we can plug back into our equation here. So what that means is that I of a is equal to I over 2 multiplied by the ln of 1 plus a plus c, and c is 0. And that one simplifies to what? I of a, which is equals to pi over 2 times the ln of 1 plus a, which is what we are asked to show. So we have been able to prove that I of a is equals to pi over 2 times the ln of 1 plus a. So when we go to the top, we see that the proof that we got is exactly the proof that we are required to find. That is this proof here. And that is by courtesy the Feynman trick, or the differentiation under the integral sign. Yeah, so that is how I solved it. So whenever you have like a parameter which you are asked to show, like you have the parameter in an integral like this, you first start by doing the Feynman trick, that is by differentiating the integral with respect to the parameter. So after differentiating with respect to the parameter, then the integral becomes very easy for you to integrate, and that is the Feynman trick. So if you really enjoyed this video, please give me a thumbs up and support my channel by subscribing to Calculus Diaries, so that I'll continue uploading engaging tutorials on integrals. I thank you, and I'll see you in the next one. Bye bye.